In this video, we're going to be taking a look at three charged particles, and we're going to solve for where to place Q2 in order to have no net force and stay at rest. So we have three charged particles. All of them are positive, which means that they're all forces of repulsion. So we're focusing on Q2. So we have a force of repulsion from Q1 on Q2, and then also from Q3 on Q2, which means that it's getting some force in this direction. We'll say an electric force from Q3, and then it has some electric force going this way from Q1. So we know that if we take the electric force from Q3 minus the electric force from Q1, that must equal 0 newtons in order for it to all balance out and for the object to stay at rest. So if you add this force to both sides, you're basically saying that these two are equal to one another. Now, if we know that they're equal to one another, we can go ahead and use Coulomb's law and a little bit of algebra to figure this out. Coulomb's law is KQQ over R squared. The problem here is we don't know what the R values are. So we know that the separation distance between Q1 and Q3 is a total of 4 meters. So what we can do is come up with our own notation. So we can go ahead and say that this distance from Q2 to Q3 is x, which means this distance over here must be 4 minus x. And there's a lot of variations you could use of that. You could have called this one x and then this one 4 minus x and so on. So let's go ahead and set up our two Coulomb's laws equal to each other and see what we can get from there. Okay, so if we go ahead and use Coulomb's law two times, it's KQQ over R squared, R being the separation distance, and the Q's being the two charged particles involved in the interaction. So if you're taking a look at the blue and green, Q1 and Q2, we have Q1 and Q2 there. Without the numerical values in yet, the separation distance we called 4 minus x, and since the equation is KQQ over R squared, we squared this entire distance. And we do the same thing with Q2 and Q3. We have Q2 and Q3 up here, and we call that separation distance x squared. So our goal is to find that x value, and if we can go ahead and find that x value, then we have our solution. So this shouldn't be too difficult because we do actually know the Q1, Q2, and Q3. And then k is the constant 9 times 10 to the 9. So let's go ahead and move some stuff around before we put in our number values. Let's go ahead and do a little bit of cross multiplying. Let's cross multiply these two because I can see that some values are going to cancel out. And then we'll have k q1 q2 divided by k q2 times q3. And then on this side, we have 4 minus x squared. And let's go ahead and use FOIL for that. So we're going to do 4 minus x times 4 minus x. We'll go ahead and do that on the side. So let's go ahead and use FOIL to find the product of those two. So the first is the 4 times the 4, which is 16. Outer, which is 4 times negative x. Inner, which is negative x times 4. And then last, which is negative x times negative x, which is positive x squared. So this is going to be negative 8x in the middle here. All right, so let's go ahead and take this 4 minus x squared and flip it up over here, but we're going to rewrite it as 16 minus 8x plus x squared all over x squared. So let's go ahead and do some cancellations here. We can cancel out this x squared. We can cancel out our k constant and actually the q2 as well. So it turns out that the actual charge of the particle we're trying to place in between these two charged particles is insignificant. So it's basically Q1 over Q2, or excuse me, Q3. So we have our Q1, which is 5 microcoulombs, divided by 4 microcoulombs equals 16 minus 8x. And that works out nicely because the microcoulombs is going to drop out, and 5 over 4 is 1.25. So we can go ahead and subtract 16 from both sides. And then we would get negative 14.75 equals 8x, and then divide both sides by 8. And then that would give us a final answer of 1.84 after we take negative 14.75. Oh, excuse me, here there's a negative over here. So this is negative 8, negative 8. So then negative 14.75 divided by negative 8 equals 1.84 for our x value. So that answers our question of our separation distance. So our x is 1.84. And if we take 4 minus that x, then we get 2.16. And because that 5 microcoulombs naturally has a greater electric field, it's going to be a little bit farther away than the 4 microcoulombs. That's going to need to be a little bit closer to have the same influence that the 5 microcoulombs has and balance out the forces so the Q2 stays at rest. So I hope that was helpful in helping you analyze the problem with Coulomb's law and solve for the position of Q2. Thank you for watching and listening.